Hey everybody, it's Mr. Canfield. I'm starting the video over again for a third time, so ignore this scratch here, it's not there. So because of the way that I've been kind of leading us into talking about integrals through these videos and in class, we're kind of doing it slightly differently than our book does. And our book does a great approach, and this is a really interesting thing. It's worth thinking through. We're going to get to the same result, but in a slightly different way. So I'm just going to kind of generally talk about a situation. So let's say we had the integral from 0 to x of f of t dt. So let's think about what's going on here. So essentially, well, we would need to know what the antiderivative of f was. And so remember in our previous video, I think it was a previous video, we talked about how the antiderivative of a lowercase f, we wind up using an uppercase f. So we'd say, well, it's f of t evaluated from 0 to x. And so there should, at least for me, there's some dissonance here. I see the x, I see the t, and I'm like, what the heck is going on here? Why do we have an x here? I'm used to seeing things like, 0 to 3 and then f of x dx. This is the kind of notation I'm used to seeing. Now the x is up here. What the heck is going on? And it's saying, given some function, if we were to integrate it and then plug in 0 and some variable for the bound, what would happen? And so what we would get is we would wind up getting the antiderivative, which we use as the capital letter. And remember that the way that works, then we drop those in and we get capital F of x minus capital F of 0. So at the outset, this might not make a ton of sense, but as we go in and start to look at some problems, we're going to see some interesting things happen here. And the thing that we're going to lead to eventually, let's see, is it here? No, we're gonna wind up talking about some sort of derivative. So, and what happens to the derivative? So we'll get there. So he says, let capital F be equal to the integral from 0 to x of f of t dt, where f is the function graphed to the right. So this right here, this is our function, and then our capital F is the integral of this, or the area of this. So he says our goal in the end is to sketch f of x. Interesting. Okay. So he says find the following. We're going to find a bunch of values, and we're going to see if we can figure out how to sketch f of x from this. So I'm going to go, you know what, I don't think, let's see, hopefully this is visible. So f of 0, oh no, I totally need this. Okay, f of 0, so that's going to be, f of 0 is going to be equal to the integral from 0 to 0 of f of t dt. Wait a minute, what's the integral from 0 to 0 of something? How much area does it accumulate between 0 and 0? We looked at other ways to prove that too. It's just 0. So f of 0 is 0. Then it says find big F of 2. So that's saying, hey, find big F of 2, and that's going to be equal to the integral from, we're plugging in 2 for x. So 0 to 2 f of t dt. So what I get to do then is look at, well, here's my function. I want to go from 0 to 2, and find that area. Oh, why does it got to be like this? So from 0 to 2, it's going to be this half of our semicircle. So let's see, our semicircle has a radius of 2, so we've kind of done this before. We know that it's pi r squared and then half of that, so divided by 2. And then we're going to take another half of that, so we just say 1/4 of pi r squared. And since the radius is 2, we wind up getting pi 2 squared, which is 4, over 4, so the 4's cancel. So the area of this is pi. You know what? The area of this is pi 2. I may as well just go through and find a bunch of these areas now. Honestly, when I do problems like this, that's kind of what I like to do. I like to find all the areas and then actually pay attention to the problems. I wonder if it'll bite me in the butt here. Let's see. So I see the area here. It's 2 blocks, so it should be 2. 1 times 2 is 2. Yep. Now this one, does that actually cross in the middle? Well, let's see. We're going from -3, -2 up to -2, 2. It goes up 4 spaces in the span of 1 unit. So yeah, that has to be the halfway point. So this right here is going to be 1/2 times base, which is 1/2, times height, which is 2. So the 2 and the 1/2 cancel each other out, and we get an area of just 1/2. And then on this one, since it's symmetric, this is also going to be an area of 1/2, but since it's underneath, it's going to be -1/2. Then over here, it's a 1 times 2, and then half of that. So that's, I said 1 times, so 1/2 times 1 times 2. So I got that this is an area of 1 here. Looks like we had another one over here. 1 times 2, yep, so another area of 1. And then, oh, that was -1 over here, right, careful. Then this guy right here is a 2 by 2, and it's half of it, so this is 2 times 2 and 1/2 out front, 1/2 times base times height, so -2 is our area down here. So now it says, hey, what's the area from 0 to 2? Well, so that means that f of 2 is equal to 2. What about f of 4? So that's just wouldn't that just be the integral from 0 to 4 of f of t dt? We're using different variables because this up here is changing, but our function is remaining constant, which is kind of strange. So let's see, f of 4, sorry, up to 4, so that's just the area here, so pi and pi, so 2 pi. So I'm going kind of fast because this is really similar to what we've been doing before. So f of 6 is going to be 2 pi minus 2, right? It's from 0 to 6, so we just add up all those areas. So now on this row underneath, though, things start to get a little bit strange, because then it says, hey, what's f of -1? Well, if we remember what's going on here, f of -1 is equal to, let's see, so we replace that x up here with a -1, 0 to -1, f of t dt. So we got to be careful here, because we're going from 0 to -1. That's not appropriate. We have to reverse the bounds, f of t dt. But when we do that, remember, reversing the bounds puts a negative out front. And so now, whatever the area we get from -1 to 0, we have to take the opposite of it, and that's what this is going to be. So that's going to be negative. Let's see, the area from -1 to 0 is 1. So we get -1. So f of -1 is -1. So I'm enjoying this process a lot more than I thought I would. This isn't normally how I teach this. I love that I'm just getting a bunch of different y values, and I'm going to be able to go in and plot these y values and find out what my original function would have looked like. It's probably going to be quite strange looking, because this is a quite strange looking function. All right, let's see. F of -2, same idea. Let's see, I have a little bit of room here. So f of -2. So since that's going to be from 0 to -2, f of t dt, same idea. It's going to have to flip-flop, go from -2 to 0, pull a negative out front, f of t dt. So, well, the area from -2 to 0 looks like that 2 plus 1 is going to be 3. So it's going to be -3. And so you might notice now that what's happening is we're able to, with -3, I can just do the area. So I shouldn't need to redo. It's the exact same process. Don't believe me, go 0, -3, flip it, take the negative out. So we're going to go from -3 to 0, and then take the opposite of it. So I do negative a half plus a half. Oh, 0. Plus 2 plus 1. So I get negative 3 again when we take the opposite. And then with negative 4, I go all the way from negative 4 to 0. So I do negative 1, those cancel, those cancel. So I wind up getting 2, and then we have to take the opposite. So I get negative 2. So if we were just to go in and plot y values, which I don't want to do on here because I'm going to need this for stuff as we continue, but let's see. If we just go, hey, let's see, all the way to negative 4, 1, 2, 3, 4, and all the way up to 1, 2, 3, 4, 5, 6. And then looks like the highest y value I see so far is 2 pi, which is a little bit over 6. So 1, 2, 3, 4, 5, 6, 7. All right, so at 0 we have 0. At 2 we have 2. At 4 we have 2 pi. 1, 2, 3, 4. So 4 is 2 pi, which is like up, that's my best estimate. And then f of 6, 1, 2, 3, 4, 5, 6. We have a slope of that minus 2. So here-ish. And then let's see. At negative 1 we have negative 1. At negative 2 we have negative 3. At negative 3 we also have negative 3. And at negative 4 we have negative 2. So the thing is, though, we don't quite know how these dots are connected. And so what we can do is we can actually find the derivative of f of x, of capital F of x. And this is where things get a little strange. So let's think about this. If f of x is equal to 0 to x f of t dt, well then it's fair to say that I can rewrite this as the integral of this, which we'll usually use as a big capital F, of x minus f of 0. And so if I do that and I think about this, well, what's f prime of x equal to? It's going to be equal to the derivative of this. And if we think about that, well, that means the derivative of this, not quite sure what it's going to be because we have these bounds in here, but we do know the derivative of this is going to be f prime x minus f prime 0. Oh, I wrote an equal sign there. Dang it. Okay, I'm reaching the end of my brain power right now. Shoot. In the middle of a video. So this, if I can't explain it simply, I don't understand it well enough. So I'm running up a little bit against some of my explanatory power because I think I have a little bit of a confusion about x's and t's. I still get them mixed up. At the end of the day, what we're going to be able to say is that the derivative of this is just going to be equal to little f of x. So I think the big deal, what I meant to talk about over here is f of 0 is equal to a number. It's some number, and in this case it's 0 in this problem, but in general it's equal to some number. And so when we take the derivative of this, we wind up getting f prime minus 0, and f prime is just f of x. So so what I'm able to do is say f prime of 4 is another way of saying what's little f of 4, right? Because the derivative of f prime is little f. There we go, my brain's back. I think I was trying to get fancier than I needed to over here. Little f is the derivative of big F, so f prime of 4 is the same as f of 4, or little f of 4. So I just go to little f and I go, hey, what's the y value of little f at 4? Well, let's see, it's 0. Oh, so now I know something about, this means the slope of f, big F, at 4 is 0. What about f prime of 2? That means little f of x at 2. Let's see. Oh, that's 2. That means the slope of f, of big F, at 2 is 2. What about at 6? Let's see, 6 looks like we're down at -2. The y value is at -2. So -2. What about at 5? Let's see, so big F prime, we just go to little f and we look at its y value. It's going to be -1. And so these are all slopes that we're given. And so if I go back in here and I'm looking at this graph, then I can say, then that means that when x is 4, 1, 2, 3, 4, and I have this y value, the slope of big F that we're trying here, it's going to be flat. So I'm just going to draw like a little, like remind myself it's like a flat. Then f prime of 2, 1, 2. So right here the slope is going to be around 2. So it's going to be 2 over 1. So it's going to be like this. And then at 6, it's going to be -2. So it's going to be that reverse. And then at 5, oh, I don't have anything at 5, but it's going to be -1. So if I look here, I'm going to have to figure out how to connect these two to each other, so it's probably going to be between those two. But now it asks me about f double prime. So let's go back and think a little bit more. So f double prime, a way for us to think about this, well, we know that f prime of x is equal to regular f of x. So what would f double prime, oops, wrong, big F double prime, it's going to be equal to this prime. Wait, this prime, so this is little f prime, right? Wait, so this picture right here is little f. What's the prime of this? Just the slope of it. So it's just the slope of our picture, of our graph. So all I gotta do is go in here and go, okay, what's the slope of my graph at 2? The slope of my graph at 2 looks like it's 0. What about f double prime of 5? Well, what's the slope of my graph when x is 5? Oh, looks like the slope is -1. So f double prime is -1. And then f double prime of -0.5 here, that's looks like it's -2. And then f double prime is 0. Oh, what's the slope right here? Does not exist. So this is allowing us to do some pretty strange analysis of this picture, just thinking about, of f without even knowing what f looks like. But now if I go back to this graph and I try dropping all those values in, let's see. Wait a minute, f double prime. What's a double prime tell us about a function? It tells us concavity. So when it's 0, that's a potential inflection point. When it's 5, or when it's a negative number, that means concave down. When it's a negative, so still more frowny face, still more concave down, and DNE, so this could be another inflection point. And so, I mean, let's see. So at 2, well, yeah, 2 we have the flat, okay. 5 we've got a concave down, and that looks like it's concave down. So I'm just gonna kind of connect those, okay. -0.5. -2. Okay, so here I want it to be like concave up, but it's telling me it's actually concave down right there. So I want to make sure that here it's looking more concave down. And then, so here, if we look at these slopes, these are going to be all positive slopes. So I'm actually going to have something concave up here, and then at 2 be flat, like no concavity, and then these are negative slopes all the way up to 4. So maybe I'll have something like that. And then let's look at my slopes here. I got a 0 slope between -2 and 1. That means no concavity, so I should have a straight line. And then here I've got a really steep positive slope. So concave up in between. Huh. Sure, and then we'll have a 0 right in the middle where f prime is. Okay. And then here, looks like we're going to have a slope of -2 again. So, another concave down situation. So, weird, but this is our potential big F of x-ish. All right, now it asks us some questions about big F of x. On what subintervals is of -4 to 6, so of this graph, is big F increasing and decreasing? So remember, big F is increasing when big F prime is greater than 0. Well, big F prime being greater than 0 is the same thing as saying what big F prime is, which is little f of x. So when is little f of x greater than 0? Here and here. So we could say it's increasing from -2.5 all the way up to 0, and then from 0 to 4. And then when is big F decreasing? Well, it's decreasing when? It's still visible enough. When f prime is less than 0. Big F prime is less than 0, meaning little f of x is actually less than 0, meaning negative numbers. When do we have negative y values? Looks like from -4 to -2.5. And then 4 to 6. So that's what's going on. Find the absolute minimum and maximum values of x on the interval. I don't think that's what he meant to ask. He must mean capital F of x. So based on my drawing here, I'm going to say we probably have the absolute max here and the absolute min at -2.5. So let's talk about how I can know this instead of just guessing based on this graph over here. So here's our original function, right? So if we start out at -4 and we're moving on, so as we accumulate, we start at -4, we're losing. Like we have this negative area, 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 negative area. Stop. Positive area, positive. So this is starting to cancel out this previous area, and it's going to keep on canceling until, so what was this, -1.5, until we hit 1.5 over here, which happens like right around here. So from here on out, I've canceled that. Now I'm adding positive area to our accumulation. Positive area, positive area. We keep accumulating positive, more and more positive area. Sure, we have like no area right there to accumulate, but we keep on getting more and more positive, more and more positive. We keep on getting more stuff. We're gathering more. And now we're starting to lose some, but we're not going to lose more than we've already gained. So you could almost think about this as like you have some level of snow, and it's melting snow, melting snow. This is like how much the snow is melting at any one given point. Then we're back to level, and now we're actually gaining volume of snow, gaining volume of snow, gaining volume of snow. We stop for a second, keep gaining more snow, keep gaining more snow. And so like the higher this is, the more snow we're gaining at that moment, but then it's tacked onto whatever was previously there. So then we lose a little bit more at the end. So the most snow we ever, or the least snow we ever have is going to be right here, and the most we ever have is going to be over here. Let's see. On what subintervals of -4, 6 is f concave up and concave down? So that again has to do with the slope of little f. So negative slopes would mean concave down, positive slopes would mean concave up. So concave down, concave up, concave down, concave up, concave down, concave down. Oh, I already did this. So easy. No, just kidding. This, for me, conceptually, I think this is very, very hard. But from like once you understand what's going on, I think it's very straightforward. So the key thing to remember is that big F of x is equal to the area from 0 to x of little f of x. The next big thing to remember is that f prime, big F prime of x, is equal to f of x, or the y values of f of x. F double prime, big F double prime, is going to be equal to the derivative of that, which is f prime of x, which is the slope of f of x. So if you get these three ideas, these problems are easy. So like I'm just going to do the first part of the homework really quick just to show how easy this can be. Complete the table. F of x, 0 to all the 8. It says f of x is equal to 0 to x of f of t. It literally is saying, hey, calculate the area from 0 to 0, from 0 to 1, from 0 to 2, from 0 to, because it always starts at 0 and it ends at it. So you just fill them all in. F prime, oh no, oh wait, f prime is just the y values. So like at 0 it's 2, at 3 it's 0, at 5 it's 0 again, at 7 looks like it's at -2. It's that fast. So if we kind of keep these in mind and then remember what we remember about increasing and decreasing all those things, we're able to use this and do a whole heck of a lot. So short section, a lot going on here. So I hope this was helpful. And oh, I just went back. I double checked his picture with the picture I drew earlier. We're basically the same. So yeah, you guys are awesome. Have a good one. Bye.